Hello, everyone. My presentation is called Life at the Edge, Marine Mammals in Hypoxic Zones. One of the biggest rising problems occurring in our oceans today is the rise of vastly hypoxic zones, which are seen throughout the entire world in many different areas in many different oceans as well. Thus, the clear purpose of this presentation is to explain what hypoxic zones are, such as how they are formed and examples of them, and deeply dive into two specific hypoxic zones, oxygen minimum zones and dead zones, which we will go to further in the presentation, and see the effect that they have on different marine mammal populations and whether or not they have evolved adaptations to combat these different types of hypoxic zones and use them to their advantage. These hypoxic zones threaten marine mammal life, but marine mammals have also found adaptations to counter the deadliness hypoxic zones have to offer. On the right side of the slide, you can also see the Gulf of Mexico hypoxic zone, which we will touch on later, and it's formed by human output and is an example of a dead zone. So before we start anything, what is hypoxia? So hypoxia is a condition in which oxygen is insufficient in the tissue level and is unable to maintain homeostasis with the rest of the body. Some major causes of hypoxia can include hypoventilation, breathing problems, or even heart problems as well. During hypoxia, the tissue cells in our body are not getting adequate oxygen delivery, which means there is a low concentration of oxygen in the alveoli in the lungs, as the oxygen is not being transported to the tissue cells through systemic capillaries. And this can be shown in image 2A, where you can see the pulmonary arteries, the pulmonary veins, and you can see a representation of how there would be oxygen traveling from the alveoli in the lungs to go out to the systemic capillaries, where it can deliver that oxygen that tissues need in order to survive. And image 2B also shows a couple of examples of what some symptoms of hypoxia are, such as rapid breathing, rapid heart rate, anxiety, and obviously slow heart rate, which can be a major indicator that there is severe hypoxia that's occurring in the area. So now that we know what hypoxia is, what does hypoxia mean in terms of hypoxic zones? So, as it states in the PowerPoint, these are oxygen depleted waters. When describing areas in the ocean as hypoxic zones, it's basically oxygen depletion. It's characterized as environmental phenomenon in which the concentration of dissolved oxygen is very low, less than 2 to 3 milligrams of oxygen per liter of water. When large areas become hypoxic, this is referred to as dead zones, which we'll talk about later in the presentation. I also love this image because it shows the Gulf of Mexico dead zone and it also shows the amount of oxygen that's there. As you can see, most of the red areas are below 1 milligram per liter. And it also shows that over the years, these areas of hypoxia have increased significantly. So now, how does hypoxia affect marine life? So from the previous slide, obviously it says less than 2 to 3 milligrams per liter of oxygen are in these hypoxic environments, which is so low. It's extremely low. So since it's so low, it's unable to support the life of many aquatic organisms, especially marine mammals. The inadequate availability of extremely low concentrated oxygen in those specific areas is not able to sustain normal marine life populations, especially the ones of huge immobile organisms such as bottom fauna, because they're immobile and they cannot move. So this is going to have a huge effect on marine mammal populations, which prey on these marine life populations. With sudden decreases in a lot of benthic organisms, and especially immobile marine life, this will only cause more problems for marine mammals, thus affecting the entire trophic level. And I love this image 5A, because it shows the entire trophic level with the top carnivores, such as sharks, dolphins, albatross, sharks obviously not being marine mammals, but it shows the trophic levels, the food web, and it shows how without the primary producers and the herbivorous consumers, it's going to be a big effect on the top of the food web if we don't have these first levels, second levels, and the primary producers in general because of these hypoxic zones. So now we're going to go on to how hypoxic zones form. So image 5A, we can see the formation of a hypoxic zone from human industrialization. So we can kind of see that although this will be focused more in the next segment, some natural ways in which some human-made ways in which hypoxia can occur is from human-induced factors. These human-induced factors include excessive nutrient pollution, which is called eutrophication, which arises from agricultural runoff and causes huge algal bloom. This comes from urban runoff, as we can see in the picture, and obviously residential runoffs and agriculture and livestock runoff. And it goes straight into the ocean, showing all the nutrient buildup that occurs into the river, creating these hypoxic zones. It creates these huge algal blooms that are unable to sustain life. And image 5b shows a naturally occurring wave, such as stratification, which can be seen in lakes. This is a naturally occurring wave in which less dense freshwater mixes with heavier seawater and oxygen, where there is a lot of at the top of the surface, but it cannot mix with the deeper levels of the deep ocean. Hence, levels 1 and levels 3 will not mix together. That's what stratification is. And it leads to the formation of these hypoxic zones through naturally occurring ways, such as seen in oxygen minimum layers, which we will talk about next in the presentation. Now, what are the two major zones we'll be looking at? Like I said before, the two major zones that experience hypoxia in their respective environments, but are very different on how they are formed, examples from our world, but most importantly, the drastic effect they have on marine mammal populations. The first zone we're going to talk about are dead zones. So these two are the two hypoxic zones as seen as 7a, dead and anoxic zone. It shows the amount of dead and anoxic zones that are kind of seen throughout the world, and we can see there's so many of them. Same with oxygen minimum layers, as there's so many oxygen minimum layers throughout the zone, specifically concentrated in the Pacific and in the Bay of Bengal in India. So now dead zones. So what are they? Dead zones, which are commonly also referred to as hypoxic zones, they're very synonymously used, are essentially the same definition of hypoxic zones, which are described above. They occur at places of significantly lower dissolved oxygen concentrations, and they occur where there's basically no oxygen in the oceans and the lakes, especially in anoxic zones, which is essentially a specific type of dead zone where there is absolutely no oxygen. Marine life is very scarcely found in these zones, and it's very rare to find it because there's literally no oxygen for marine mammals and marine organisms to use. And due to these extremely lessened oxygen conditions, many organisms cannot survive, and it impacts marine life in a huge way. And I have a fun little picture showing that there's danger, no oxygen, you don't want to come in here. So if there's no oxygen, how can marine life and marine animals survive? Well, we're going to see. So now we're going to go really deeper into how these dead zones are formed. If you remember earlier, they're really formed from human-induced factors such as excessive nitrogen, and eutrophication is the name of when dead zones begin to form, when excess nutrients, primarily nitrogen and phosphorus, are going to enter the coastal waters and they're going to help fertilize blooms of algae. And this is what eutrophication is. These excess nutrients, excess nutrients, sorry, are being washed into the ocean because of human activities such as agricultural runoff, as explained before, and these organisms, which we can kind of see over here in the image, with such as phytoplankton and algae and seaweeds, are going to really grow quickly, and they're going to, excuse me, they're going to really grow quickly, and they're going to be really excessively on the surface of the water. This rapid development of algae and phytoplankton is what is referred to as the algal bloom, as it creates the dead zones below them. The image on the left shows this beautifully, as when the algal bloom, sorry, is produced, it prevents light from penetrating the water surface and thus does not allow oxygen to be absorbed by organisms beneath them. As these algae also die, bacteria would decompose the algae that is dead, and this also requires a lot of oxygen. That's the big key. Algal blooms require a lot of oxygen, hence we're not going to have a lot to spare. And bacteria decompose the algae and it creates these really hypoxic filled environments. So now that we know how dead zones form, what are some major examples of dead zones? So some of the major examples of dead zones include the Gulf of Mexico, which is the largest in North America, the Baltic Sea, the Black Sea, and the Chesapeake Bay. So specifically looking at the Gulf of Mexico, like I said, it's the biggest one in North America, and it is caused through the excessive nutrient overflow in the Mississippi River, specifically phosphorus and nitrogen, causing eutrophication to occur and thus the formation of the huge dead zone. So as you can see in the bottom right picture, in image 10b, that's an image of the Gulf of Mexico. That's how it looks like with these really big algal blooms. And if we can go back to the previous slide, then it's going to really show these algal blooms are occurring due to the nutrient runoff, the human-induced factors. That's why it occurs. And image 10A also shows that in Chesapeake Bay is also a really large dead zone, and it also occurs for the exact same reasons. So now we know what major examples of dead zones are. What effect do dead zones really have on marine mammals? So, major effects on marine mammals. Dead zones obviously have a huge effect on marine mammal populations, although they are synonymously used with hypoxic zones, as hypoxic zones will eventually create dead zones. They differ in one huge way because dead zones are caused by human-induced factors, and these zones have little to no oxygen, which can also be characterized as anoxic zones. Human factors which cause dead zones is a primary factor of why dead zones will never cease in parts of the ocean, and the cycle will also continue. This is where I found a quote from a really important study, and it says, "Self they refer dead zones as self-sustaining vicious cycles taking decades to reverse." So this kind of shows how no matter what happens, it's always gonna like have an important part in the ocean, and the dead zones are never essentially gonna go away. And the article again explains, as a result, the total amount of nutrients, phosphorus and nitrogen in the water will remain, as even as high inputs have been reduced. And again, it's a self-sustaining vicious cycle. This is a huge reason why it's been a severely negative impact because of the environmental toxicity of the water due to the significant nutrient pollution from obviously humans. And this is compared to naturally occurring hypoxic regions in which marine mammals have developed physiologically, physiologically adaptations to these hypoxic regions, which we'll obviously discuss later. And this severely decreases the marine diversity as explained in the PowerPoint and that the many fish populations, and it steers marine mammals from really wanting to come in these overexpanding dead zones. So now we can see in the infographic, it kind of shows when there's severe agricultural runoff, it's going to cause huge algal blooms, which will obviously overall cause marine life mortality to increase. So image 11A kind of shows a pileup of fish in a dead zone. I believe this is the Gulf of Mexico, and it kind of shows like the amount of fish that just died just from the toxicity. You know, the environmental runoff, the toxicity that these toxic environments can create and these dead zones can create. And image 11B is probably one of my favorite, and it really shows the huge algal bloom formations. And obviously, with the green color, it kind of looks like that, but it shows how deadly these algal blooms can be. Although it looks very mesmerizing with the green, they are very, very deadly, and they can have a huge effect on marine mammals. So one way it can have it is because they can lead to the death of marine mammals and shorebirds that rely on this marine ecosystem for food. And marine mammals such as sea lions, dolphins that depend on fish for survival, they can't because if there's fewer fish beneath the algal blooms, then the animals lose an important food source, and thus this limited prey will lessen the survival of marine mammals. So now we're going to talk about the effects that it has on marine mammals continue. So there's been some major trends that I've seen in marine mammals. So some major trends are that there are major habitat shifts in marine mammals as they will leave habitats for more oxygen-rich areas. There's a disruption in their foraging patterns due to decreasing prey availability and feeding efficiency. And there's an increase in marine mammal mortality due to excessive nutrient pollution, like I said before, with the phosphorus, nitrogen coming from human-induced factors, and the continued existence of extreme algal blooms, which can cause huge, huge problems for marine life. And then there's also major trends for just marine life in general, which obviously have an indirect impact on the life of marine mammals. So for major trends in marine life, they have major decreases in the trophic level efficiency, reducing levels of the food web and ecosystem productivity. And they also have substantial mortality rates for benthic organisms and overall low trophic marine organisms. So now that we know what the effects are in marine mammals, can marine mammals have any adaptations to survive through these dead zones and anoxic zones? So the short and simple answer is yes, but no. So what this means, so obviously marine mammals have developed many adaptations for diving in hypoxic zones, such as increasing body oxygen storages, regional vasoconstriction. There's so many things that we're going to talk about in oxygen minimum layers. However, these adaptations are not suited for the chronic environmental hypoxia, which I love to call it, and the article says that these dead and anoxic zones have in the Gulf of Mexico and the Baltic Sea. If it's an anoxic zone and there's no oxygen, how can you survive? Well, it's a trick question because you can't. It's called chronic environmental hypoxia because it's never going to go away. And like the previous article said, it's a viscous cycle of repeat. So lots of research has been done on the direct effects of dead zones that they have on marine mammals, and thus whether or not they can adapt. However, while some marine mammals themselves may still be able to survive in these heavily, heavily dead zones, a huge magnitude of other marine organisms can't, which causes this large habitat degradation and populations to decrease as well. A specific study in the Frontiers of Marine Science looked into this phenomenon and did a study on the effect of extreme hypoxic zones for Indo-Pacific humpback dolphins. And the results of the study kind of showed that there's persistent low populations of these humpback dolphins in these hypoxic regions compared to the non-hypoxic regions. This continues until 1 month after hypoxia. It really shows how that the only thing that those humpback dolphins can do is just change their habitat. They can migrate to these non-hypoxic zones, even though they might have the adaptation to survive, but they still choose to migrate to these non-hypoxic zones because there's so much uninhabitable life. So, as explained by the previous studies and the major trends in marine mammals and life in dead and toxic zones, places like the Gulf of Mexico or Baltic Sea are very far from places marine mammals would like to stay in. These extremely deoxygenated zones, persistent with excessive nutrient pollution and formation of algal blooms, are uninhabitable for many forms of marine life, as I said earlier, and thus create a negative effect on key marine mammal populations, such as the humpback dolphins, humpback whales, sorry, humpback dolphins, sorry, that we just discussed. Now, the image on the right for image 13A shows the distribution of Indo-Pacific humpback dolphins, and I really love this because it shows how on the coast it's really close. It shows the sighting rates with its high, low, reserve, and hypoxic zones. And hypoxic zones are more kind of deeper. They're not on the coast, but they're kind of deeper into the waters. And it shows how there's literally zero sightings for these marine mammals, these dolphins. They all are kind of closer to shore where there's very high sightings, there's low, but they're not in the hypoxic zone, showing how they just rather be closer to the coastal waters than kind of be in those zones because of how toxic they are, because of how environmental chronic they are. So that kind of explains dead zones and the real effect they have on these marine mammal populations. Now we're going to kind of go on to the second hypoxic zone I mentioned at the start of the presentation, oxygen minimum layers. So oxygen minimum zones or oxygen minimum layers, they are a type of naturally occurring hypoxic zone. They are persistent layers in the water column that have oxygen minimum layers in regions where the dissolved oxygen is much lower than at other regions in the oceans, typically falling to under 2 milligrams per liters, when the average could be about 4 to 6 milligrams per liters. These oxygen minimum zones typically occur anywhere from a broad range of 100 meters to 1,500 meters in depth in the ocean, and they're typically said to be called a sandwich of layers as they can be between very high concentration of oxygen, which is obviously going to be at the surface, and then a very low concentration of oxygen, which is going to be in like the really deep oceans. And I have a funny infographic on the bottom left, which kind of just shows the greeting of oxygen minimum zones and them saying stop because obviously there's very less oxygen. And image 14A really just shows this oxygen minimum layer. Obviously, it can occur anywhere from 100 meters to 1,500 meters, but it shows how it just kind of persists as this one layer in the ocean, obviously created naturally, which we will discuss after, and it kind of persists there as a sandwich. So, oxygen minimum zones, how do they form? I love this image. It really shows one natural cause of how these oxygen minimum zones form. They are very different from hypoxic zones, specifically numerous dead zones, that they are naturally occurring and they're not made from the byproduct of human activities. These zones are created due to a series of biological, chemical, and physical processes. So, for example, this image kind of shows how some of the oxygen minimum zones are usually located in areas of upwelling in which there are lots of nutrients available, and it's going to eventually cause a phytoplankton boom, as we can see in the image, and it's going to cause the sinking and decomposition of organic matter catalyzed by bacteria, which consume a lot of oxygen, thus creating the oxygen minimum zone. The image, we can see how it says oxygen O2 flux is blocked, which is like in the middle, and obviously like there's three different zones with the phytoplankton boom happening on top. So it kind of shows the decomposition of this organic matter and how essentially it's made. Now, oxygen zones can also form because of the stratification in the water column, which essentially means that it prevents against the mixing of the different water layers. This is a common theme found in many oxygen minimum zones, and it reduces the mixing that can be available between the surface of the ocean with high oxygen, obviously, in the deep part of the ocean that really has a lesser amount of oxygen persisting for a long period of time. So now that we know how these oxygen minimum zones form and how they're different from dead zones, let's talk about what are some major examples of these oxygen minimum zones. So some major examples of oxygen minimum zones are the eastern, southern Pacific, and the eastern tropical North Pacific, the Bay of Bengal, which sits right below India, and the Arabian Sea. Now, both these images I love because they kind of show comparison of these oxygen minimum zones around the world. The biggest ones, like I said, being in the Bay of Bengal and the eastern Pacific, and it kind of shows the amount of oxygen saturation that's at depth in these zones because oxygen minimum zones are at a specific depth. So it kind of shows the amount of oxygen that is kind of there. And now that we know where oxygen minimum zones occur and we can see the depths at which the oxygen saturation levels are, what effect do these oxygen minimum zones really have on marine mammals? Is it different than dead zones? Let's check it out. So oxygen zones and their effect on marine mammals. So oxygen zones have a huge effect on marine mammals. In this case, similar to the previous example of dead zones, they do have a drastic negative effect on marine mammal population as well, but they also have positive effects as well. Although not synthesized by human-induced factors such as agricultural runoff or an excess of nutrients, oxygen minimum layers are one of the most deoxygenated zones in the ocean, having very little and sometimes no oxygen as well, and very specific anoxic OMZ layers. So specific studies and articles in major OMZs give examples to show different effects oxygen minimum zones have on the marine mammal populations, and these major trends include vertical compression of marine mammal habitat, changing/decreasing prey availability, and increased competition among marine mammal species, leading to high stress. So what are the first two essential points mean? So I love this infographic, image 17a. It kind of shows the vertical compression that can happen in these oxygen minimum zones. And because the middle of the zones are really filled with these deoxygenated oxygen with very little to no dissolved oxygen, it's going to force the prey to either go up or down. Like I said, it's going to force the habitat compression where the prey can go down. It's going to also form like squid, for example, which is a major prey that many whales have. It's going to form them to go up. So it's going to kind of help them. And in fact, which I'm going to talk about later. And also, there's obviously going to be negative effects such as decreasing prey availability because even though it creates this vertical compression, there's still going to be prey that just can't survive in these very oxygenated, low oxygenated waters. So now their effect on marine mammals continued with the negative effects compared to the positive effects. So some negative effects that the oxygen zones have on marine mammals is the decreasing prey availability, like I said earlier, which comes with just oxygen-derived layers, and also the increased competition that comes from marine mammal populations in finding the prey as they all may be clumped up in one area. Now, I said that could be a positive thing, but that also could be a negative thing because you're kind of all fighting for like similar type of prey all in the same area, you know? And like I said here, the OMZ is no joke. There's very little oxygen that's available, and it's a full vertical region consisting of just no oxygen, or little to no oxygen. Thus, many of the marine life population in general, especially in mobile marine mammals, marine life suffers very high mortality rates, or they migrate to different habitats, decreasing the availability of prey. Thus, this would increase the competition of marine mammals for this limited prey, driving many psychological stressors for these marine mammal populations. However, there are equally as many, if not more, positive effects that kind of happen from these oxygen minimum zones, and it's the changing prey availability and how this affects the vertical compression it induces for many marine mammals' habitats. So, many small organisms which cannot survive in the region of the OMZ will also become vertically compressed, which would be a benefit for marine mammals, though certain species that will accumulate in a specific vertical region, which would actually enhance marine mammal foraging as a result. Studies reported for a deep diving northern elephant seal, Morongo Anostracis, which I'm going to show a really good picture for in the next slide. They, and even sperm and beaked whales, suggest that low oxygen concentration could really reduce the overall prey motility and not be able to move that much, which leads to an enhanced foraging for marine mammals as a result. These studies suggest that greater prey density due to the compression of the vertical prey distribution will reduce diving costs and make it much more efficient for marine mammal populations to dive. So we're going to see this in the next image, and I really love this image as well. Image 19a because it captures They're ragfish. Now, these ragfish, the specific name of them is called Isoetus angiometus. And there's three different images compiled into one. And with image A, it kind of shows the green ones are the the green ones are the specific deep diving northern elephant seals, the Mergana under stress that I mentioned before. It's when they capture these ragfish, and it's like the success that they have and what depth they capture them. So obviously it's at a very like low depth, 790 to 800, where a typical oxygen mammal layer can form. And then B and C shows video proof of them capturing this ragfish. And the reason why it's so significant is because this is a very specific and rare kind of ragfish. It's only found in these very oxygenated, very deoxygenated waters, very low concentrated waters, and it's theorized that they really can't move. Like that specific species is just kind of staying there. It's not going to go up, it's not going to go down. It's going to like reduce the prey motility, which allows these North elephant seals to really like capture them and use them, which shows the enhanced foraging that kind of comes with it. But wait, are some of these effects similar to the ones found in dead zones? Yes, these are very similar to some of the same stresses found in dead zones, that is a very common theme in hypoxic regions. The key difference is just one thing. Marine mammals have found a way to exploit these oxygen minimum zones, and many populations have monumental adaptations which allow them to not only survive in these hypoxic oxygen minimum zones, but succeed and develop diaphysiology, which helps them survive. That is the biggest difference between oxygen minimum zones and dead zones, the marine mammal adaptations, because dead zones, like I said before, are just too chronically, environmentally, just low depleted oxygen. Because of the human induced factors, it's not going to be in a position where marine life and especially marine mammals can really survive, and they induce really high mortality rates. So what are some major marine mammal adaptations that occur in these oxygen minimum zones? There's four of them from major studies: high levels of hemoglobin present in cells, huge capacities of myoglobin in muscle cells, repeated episodes of ischemia, and enhanced removal of oxygen from water. So these are huge adaptations, and unlike the chronic environmental death zones, like I said before, they really have these adaptations for hypoxic zones, and they use it for their benefit. So the main theme from what I just said is really how marine mammals adapt to these hypoxic oxygen minimum zones through the expansion of their body's oxygen storage. The oxygen storage in the body is such a huge thing, and it's a reason why these marine mammals can really adapt and survive in these depleted oxygen zones, like hypoxic zones and OMZs. Marine mammals do this primarily due to their high concentration levels of myoglobin that they have in their muscle cells. So studies such as the one on the pinniped skeletal muscle cells, which I will show a picture of in the next slide, really shows that myoglobin plays an important role not only as an oxygen source, but also in the facilitated diffusion of oxygen through the muscle, especially under hypoxic conditions. It also explains that increased myoglobin concentrations help increase the volume density of mitochondria, which increases the diffusing capacity of skeletal muscles and allows for the increasing aerobic respiration even under these conditions, allowing for pinnipeds to survive under extremely hypoxic conditions in these oxygen minimum zones. So these myoglobin concentrations are higher in the specific muscle cells that require those more oxygen during the swimming, which is going to be shown in the next slide. Now, there can also be some more adaptations in the body oxygen storage through hemoglobin. So there's elevated hematocrit and hemoglobin concentration levels, and this can primarily happen through the contraction of the spleen, which increases the amount of oxygen red blood cells in storage, and also through the increase of the amount of red blood cells in the blood, which allows O2 to cooperatively bind and have a higher affinity for oxygen at very specific points in marine mammal diving into these oxygen minimum zone hypoxic regions. Now that we talked about how it affects how the adaptations are for the body oxygen storage, we can talk about ischemia and bradycardia. So these are other adaptations that marine mammals have had, and marine mammals have adapted to ischemia in their response to low oxygen concentrated waters by repeatedly just tolerating these episodes of ischemia during longer parts of the dive in order to successfully optimize the specialized compartments of their body, which need a larger oxygen storage, such as the heart and the brain. Obviously, when there's in these oxygen depleted waters, you cannot just go from the capillaries and the tissues cannot each get an equal amount of oxygen. Thus, ischemia or vasoconstriction, that is also called, is a very specific specialized process in which you only compartmentalize the body, which really needs the oxygen. And obviously, the heart and the brain are probably two of the major ones that really need this. So this ties in bradycardia as well, as marine mammals will decrease the heart rate and they will conserve their oxygen so it's not consumed as much. So there's specific studies that explain that marine mammals do not really suffer ischemia/reperfusion events that are seen in humans, but they still cope through the tissue damage that's sustained in these events. And a specific study explains that cetaceans may have actually evolved mechanisms to deal with this ischemic inflammation through contracted gene families involved in acute inflammatory response and repair of lipid peroxidation. So both of these examples, yet again, just show how these adaptations of marine mammals to survive in these long vertical hypoxic oxyminimum zones and how they can survive and how it really kind of goes with their diving physiology as well, because all of these come from how well they can dive into these hypoxic zones, but still come back up. So these kind of really show the adaptations that these marine mammals really have, specifically in oxyminimum zones compared to like dead zones where they really can't do it. So to kind of go over this next part, this is the image that I was talking about, so image 22A, and it kind of shows the myoglobin concentration in swimming and non-swimming mussels. And as you can see on the right-hand side, for example, harbor seals, they have a 37.4 myoglobin concentration in swimming, and in the non-swimming muscle, which is called the pectorals, they only have a 24.1. So it kind of shows how there's elevated myoglobin concentration levels in the swimming muscles, which makes sense because these myoglobin concentrations are used as other storage compared to the hemoglobin that we already have, and it's able to provide just more oxygen when marine mammals are diving. That's the key. More oxygen in these severely depleted oxygen zones, obviously. So now, to kind of wrap it up, conclusion, what have we all been talking about? What are the key points to take away if you haven't been paying attention to the presentation, which it's a very long one, so I don't blame you, but these are the key points. So hypoxic zones, which we talked about at the very start, they form from depleted oxygen levels less than 2 to 3 milligrams/milliliters, and they form two major types of zones, oxygen minimum zones and dead zones. Dead zones are formed from human-induced factors, creating a chronic environmental zone such as Gulf of Mexico or the Baltic Sea dead zones. Now, these dead zones, they affect marine mammals through habitat shifts, foraging patterns, and algal blooms, which really cause this irreversible damage to this marine life and marine mammals. So while there can be adaptations, there are no true adaptations from marine mammals to dead zones because they can be very anoxic and extremely uninhabitable for all types of marine life. Now, on the flip side, oxygen minimum zones are naturally occurring hypoxic zones under 2 milligrams per liter and are seen heavily in the Pacific and the Bay of Bengal. They cause both negative and positive effects, as I discussed earlier, but the main key is marine mammals can adapt, and they can adapt through these high levels of hemoglobin, myoglobin in the muscle cells, ischemia, which is also called vasoconstriction, and bradycardia, and the removal of oxygen from water, which is also very important. And this really depicts the marine mammal diving physiology and the adaptations to these hypoxic-driven oxygen minimum zones around the world. And it shows the effects that these hypoxic zones have on marine mammals and how they can adapt. And if they can adapt, why can they not adapt? So thank you for listening to my presentation. These are the references, and I hope you learn more about what hypoxic zones are, what are the two major types with dead zones and oxyminimum zones, and how they really affect marine mammals, and whether or not marine mammals can adapt, which, as you can see, in oxyminimum zones, they can. Thank you so much for listening.